Going to explore the idea of proof by contradiction, also known as indirect proof. We've looked at direct proof already. Also known as reductio ad absurdum, which is not some Harry Potter spell that transforms its victim into a creature with eyes where its ears should be and gummy worms for fingers or something, but it means reduction to absurdity. And the idea here is that we assume that a statement is false and show that that assumption leads to a contradiction or leads to something absurd. And so that's what we're looking at. And so our target today is to prove the truth of a statement by showing that the negation of its conclusion results in a contradiction. So when we talk about the negation of the conclusion, I'm referring to conditional statements in the if-then form, where the if part again is the hypothesis and the then portion is the conclusion. And we are assuming that that conclusion is false and seeing where that leads us. And if the original statement is true, then by assuming that it's false, we will arrive somewhere down the line at a contradiction, a situation that cannot be, and which implies that the original statement must be true. So as our first exercise, we want to prove that the square root of 2 is an irrational number. So when we think about irrational numbers, we want to go to definitions. And the definition of irrational, think about that. If I ask you to define the word irrational, the first thing that might pop into your head is not rational, right? And so that's a clue to us. If the thing that we're trying to prove is the negation of a definition that we can describe more easily, then that might be a good candidate for proof by contradiction. Because what we're saying here is prove that the square root of 2 is not rational. That sounds a little bit difficult to do. What if we assume that the square root of 2 is rational instead and see where that leads us? And that's our strategy here. Assume that the square root of 2 is rational. Why is this easier to work with? Because the definition of rational is something that I can more easily write than the definition of irrational. And when I say that it's easier for me to write, I mean symbolically, mathematically. I can write that the square root of 2 is rational by realizing that when I say the word rational, I mean to say that a number is a ratio of two integers fully reduced. And so I can write that the square root of 2 is a ratio of two integers, a and b, such that a and b share no common factors. The key here about the sharing no common factors is that we want to say that the square root of 2 is a fraction that's fully reduced. And so that'll come into play later. You'll see why. But it doesn't, we don't lose any generality there when we say that a and b share no common factors, because any fraction that we had, if it were reducible, we would be able to reduce that so that a and b did not share any common factors. Okay, so we have written here that the square root of 2 is a fraction of two integers. We know that it's not true, but we need to see where this assumption leads us, what contradiction we're going to run into by saying that it is true. So let's do some algebra. Alright, well, if the square root of 2 is a over b, then clearly if we square the fraction a over b, getting a squared over b squared, we will have 2 itself, right? And that means that a squared is equal to 2 times b squared. Clearly that means that a squared is even, right? Because a squared is a multiple of 2. However, it also implies that a itself is divisible by 2. The reason for that is that if a squared is divisible by 2, then we have two situations that are possible. Either a itself is divisible by 2, and when we squared, a squared would still be, of course, divisible by 2, or a is not divisible by 2, which would mean that the only way that a squared was divisible by 2 would be to have a factor of the square root of 2, so that when we multiply a by itself, a squared has a factor of 2. However, we know, because we've defined it such, that a is an integer, and so a can't have an unmatched square root of 2. We don't know that, we're trying to prove that the square root of 2 is rational, but we can certainly say that the square root of 2 is not an integer because we know, the integers are a well-ordered set, and we can square each of the integers, and none of the integers squared give us 2. So we know that the square root of 2 is not an integer. So take a minute, absorb this. A must be divisible by 2 if a squared is divisible by 2 and a is an integer. Okay, this is a key notion here. So where does that lead us? Well, if a itself is even, then a squared must be divisible by 4. So we can rewrite a squared as 4k for some k where k is some integer. So I'm saying here in this statement that a squared is a multiple of 4, and the k is just standing in for that multiple. Well, if a squared is equal to 4k and a squared is equal to 2b from the step before, well, we can say the 4k must be equal to 2b squared. Excuse me, a squared is equal to 2b squared. Therefore, 4k is also equal to 2b squared. And dividing both sides by 2, we see that b squared is equal to 2k. Well, this implies that b is even for the same reason that a was even above. And here's where we run into our contradiction. Because we had said on the outset that a and b share no common factors. But if a and b are both even, then they share the factor 2, which contradicts our original statement. Therefore, the square root of 2 must be irrational. Let me make some points here. The reason that we can say that the square root of 2 must be irrational after what we've done is that we have started with a simple assumption. We have performed only correct mathematical steps beyond that. So we've done everything correctly. We've made no mistakes, and yet we've arisen to a point where something can't be true. Two things can't simultaneously be true. It can't simultaneously be the case that a and b share no common factors and a and b are both even. That is what is absurd. That is the contradiction. But we've made no mistakes in our math, in our steps. That implies that the only mistake possible is in our assumption, our original assumption that the square root of 2 is rational. So this assumption must be incorrect if all of the rest of our steps are correct, because we've arisen at a contradiction. And so, given that there is a mistake, and the only place that mistake can exist is in the assumption, it must be the case that this assumption is wrong, and the square root of 2 then is irrational, not rational. And that's the heart of a proof by contradiction. Performing a series of correct mathematical steps based on an assumption and arriving at something that doesn't make sense. This implies the assumption originally was wrong. Let's look at one more example. Prove there are infinitely many primes. Again, think about that. Can you prove that there are infinitely many primes? Why don't you list them all? That's something really hard to do directly. We can't ever list the infinite primes. And again, what does infinite mean? Not finite. So let's look at this indirectly as a proof by contradiction. We'll assume that there are a finite number of primes. If there are a finite number of primes, well, then there must be a largest one, and so let's define a variable to represent that. Okay, so we've got a finite number of primes. We're going to say that x sub b is the largest of those primes. Okay. We're going to let lambda equal the product of all primes plus 1. So again, x sub b is the largest prime. Lambda is going to be the product of all of the primes. So we're going to let the set x here be the set of primes. So x sub 1 is the first prime, which is 2. X sub 2 is the second prime, which is 3. X sub 3 is the third prime, which is 5. All the way up to the final prime, the largest prime, x sub b. And we're going to take that product and we're going to add 1 to it. Think about lambda for a minute. Lambda can't be divisible by 2. Why? Because this product is a multiple of 2. And we've added 1 to that product. So no number no number is both a multiple of 2 and one more than a multiple of 2. So lambda can't be a multiple of 2. Likewise, it can't be a multiple of 3 because we've got a multiple of 3 plus 1. Nor can it be a multiple of 5, nor any of the primes. So we have a situation here where lambda is not a multiple of any prime. And what does that mean for lambda? Well, that means lambda must be prime itself. But lambda is one more than the product of all of the primes. And the product of all the primes is greater than the largest prime. What this means is we found a prime number, lambda, that is greater than the largest prime. So we found a prime greater than the largest prime. Well, that's a contradiction. X sub b can't be the greatest prime because lambda is greater than it. Well, this contradicts our statement that there are there are a finite number of primes. So this assumption must be incorrect, and there must be infinitely many primes. There are other ways to prove these things, but these are two classic proofs by contradiction. Think about the problems on the worksheet and come in tomorrow ready to work on them.